Hello guys, my name is Uday. Today I'm going to explain you about my assignment 3. There are six to six questions. So I'll explain you question one by one. For each question, like 1 minute. So the first question is elbow in VIEs and diffusion models. Let us understand elbow or the evidence lower bound in variational autoencoders. The goal is to maximize the data likelihood log P of X, which is often iterable. Instead, we optimize the elbow uh, the elbow equal to EQ of Z by X or into log of P of X by Z minus divergence, scale divergence, which is Q of Z by X on P to P of Z. The first term is the reconstruction likelihood measuring how well the model reconstruct the input data. The second term is the KL divergence, which regularize the latent variable distribution to match a known prior. Now, in diffusion models, elbow also appears but in a different way. The models add noise step by step and learns to reverse it. The elbow here guides the training of the reverse process by approximating the true data likelihood using a variational distribution over noise steps. So, in both VAEs and diffusion models, elbow helps us to learn generative models by providing a tractable surrogate for a log likelihood. Now I'll explain the second question, which is understanding the beta VAE objective. In a standard VAE, the objective is to maximize the elbow. You know that LVAE equal to EQ Z by X of log P of X by Z, where minus KL divergence of Q of Z by X to P of Z. This balances reconstruction and regularization of the latent space. The beta VAE modifies this by adding a scaling factor beta L beta VI equal to EQ of Z by X log P of X by Z minus beta into KL divergence Q of Z by X plus P of Z, where beta, if greater than 1, the model emphasizes the disentangling the latent variables, leading to more interpretable features. The lower beta is the better reconstruction, but entangled representation. Thus, the beta controls the trade-off between the reconstruction quality and the independence of the latent factors. This is useful for interplay and transfer learning, especially in unsupervised settings. The third question is like understanding the diffusion process in generative models. The diffusion models generate data by reversing a gradual noise in the forward process. The Gaussian noise is added to the data over t steps. That q of xt by xt minus 1 equal to natural number n into xt, the square root of 1 minus beta t xt minus 1 comma beta t into I, which I is an number. This creates a sequence from a clean data x0 to pure noise xt. During the training, will learn the reverse process. The p theta of xt minus 1 by xt equal to n of x t minus 1 mu theta of xt comma t sigma 0. We maximize a variational lower bound or elbow between the forward and reverse trajectories. In practice, the model is trained to predict the noise. L simple E of epsilon minus epsilon theta of xt of t of square. At inference time, we start from noise and apply the learner denoising steps to generate new data. This process enables high quality and controllable data generation. Now the script for Gaussian VAE loss and reparameterization question. A Gaussian VAE models the encoder as Q naught of Z by X into N into mu to sigma square. As a prior, the PZ equal from 0 to Y. The VAE loss function is the negative elbow. The loss of VAE equal to uh, absolute X minus X caps whole square plus 1 by 2 sigma J equal to 1 to D of mu J square plus sigma J square minus log sigma J square minus 1, which is the reconstruction loss plus scale divergence. The first term ensures the decoder reconstruction the input. The second term aligns the latent distribution with the prior. To compute gradients to the sampling step, we use the reparameterization trick where z equal to mu plus sigma into uh, sig alpha. This makes z a deterministic function, enabling end-to-end training together. The components make the VAE trainable using back propagation. And the other question is like importance of learning GANs, VAEs, diffusion models, and transformers. In spring 2025, learning GANs, VAEs, diffusion models, and transformers is crucial due to the explosion of generative AI. The GANs are powerful for generating realistic images and widely used in creative industries. VAEs provide structural latent representation, enabling abnormality detection and disangle learning. Diffusion models have become the state of the art for image and video generation with stable training and high quality. The transformers are the foundations of modern AI, powering large language models and the visionary language systems. This course gave me hands-on experience, deep theoretical understanding, and project guidelines. Now I feel confident to build real-world generative systems and contribute to research. In the future, I intend to apply these skills to develop AI tools, publish research, and work in cutting edge generative AI roles. And the fifth question is like key learnings from the research papers. In the auto encoding variational bias by Kigma Welling taught me the elbow variational inference and the reparameter essential for training VAs. The introduction to VAs tutorial explained the Bayesian concept and helped me to understand that latent variable models in depth. The beta VAE introduced a distangled representation of learning by scaling the KL term. The trading of reconstruction for interpretability DC GAN demonstrated the stable convolutional architectures for GAN useful in visual generation tasks. DDIM showed how to reduce sampling in diffusion models while maintaining quality. The survey on diffusion models gave me a broad understanding of noise schedules, guidance, and use cases across imaging and vision. Emily Denton's GAN survey helped contextualize the evolution and practical challenges in GAN training. FGAN generalized the GAN framework through F divergence, broadening my view of adversarial training objectives. VQVAE and FSQ introduced discrete latent modeling and quantization strategies for scalable generative model. The protein structure paper introduced how deep learning is transforming structural biology through tools like AlphaFold. The robust VAE likelihood for outlier detection taught me practical considerations and corrections for bias in generative model scores. The improved techniques for GAN by Selman's and his teammates provide a trick to feature maturing and mini batch discriminations to stabilize GANs. Together, all these papers shape my understanding on VAEs, GANs, and diffusion models and transformers, preparing me to build real-world AI tools and pursue generative AI research. So this is my analysis of theory questions. Thank you very much.